So the first talk is Higher Chern Correspondence by Roberto Téllez from ICMAT.
So first of all, thank you very much for giving me the opportunity to speak here. I am Roberto Téllez Domínguez, and I am a student of Mario García Fernández and Luis Alberto Consul. So I'm going to work about some work that we've been doing for my thesis, which is related to two principal bundles. So the previous talk was about GERFs. GERFs, as Severin pointed out, can be thought of as principal bundles for certain abelian Lie groups, and I'm going to talk about the non-abelian case. So this is the outline of the talk. First, I will give some motivation on why we think this problem is interesting. And then I will speak again about GERFs, which is going to be the language for what's coming next. And then I will be able to describe Lie2 groups and two principal bundles in terms of GERFs. So it's important to understand GERFs very well. And finally, we will have some conclusions on all this. So what's the motivation? We can consider the Hull-Strominger system, which is a system of partial differential equations that one can define over a Faraday manifold, possibly non-Keller, so X is a complex manifold, and omega is a holomorphic volume form with a Hermitian vector bundle. And so it's a system where there are two unknowns. One of them is a unitary connection on the Hermitian bundle, and the other one is a Hermitian metric on the manifold. And well, this is the set of equations. And as we know, this is an integrability condition on the connection, on this connection. And what we are going to do is to interpret this second equation as an integrability condition on a higher principal bundle. And this is based on a certain recent paper by Mario García Fernández, Roberto Rubio, Carl Tipler, where they have interpreted this system in terms of horizontal lifts on string current algebras. And this has allowed them to interpret the rest of the equations through a moment map, and thus constructing a modulus space of solutions. So this is a sign that this is related to higher gauge theory, because current algebroids are usually believed to represent infinitesimal symmetries of higher principal bundles. This was pointed out in Severin's talk for the case of abelian GERFs and exact current algebroids. And the more general statement is that general current algebroids should represent infinitesimal symmetries of general principal bundles. So what we're going to do is to develop a theory of holomorphic principal bundles in this higher context and connections on them through the language of GERFs. And we will obtain a Chern correspondence for connections on these holomorphic principal bundles that will allow us to reinterpret the Hull-Strominger system. So let's begin with the language of GERFs. I'm going to define a GERF for T and an arbitrary abelian Lie group. And as Severin pointed out, a GERF is a certain higher differential geometric object, but it can be described very simply in terms of certain cocycle data. So the GERF will be given by a 2 cocycle. This is 2 cocycle. And I will say that this GERF has a connective structure if I have one force on the double intersections satisfying this condition. And I will say that it has a curving if I have 2 forms on the open set satisfying this relation. So this is what Severin called a GERF with connection. But my point of view, and I'm sorry for this, but my point of view is going to be slightly different related to what he said on the second part of his presentation. So for me, what the object that has to be thought as a bundle is the GERF with connective structure. And the curving is a connection on it, which makes sense because of the kind of stuff that Severin was talking about. And it's related to generalized geometry because of this fact that you can associate an exact current algebroid to a GERF with connective structure, but you have to choose one. And yeah, once I have this data, I can define the curvature of the GERF, which is a free-form, a global free-form next, defined in this way. And yeah, because I'm going to work in the holomorphic context, I will say that if my abelian group is holomorphic, complex, the GERF will be holomorphic if the cocycle is holomorphic. The connective structure is holomorphic. This will be important for me. And if I will say that the curving is compatible with this holomorphic structure if it's given by two zero forms. So this is what a GERF is, and when we define a geometric object, we also have to define what are their isomorphisms. And if a GERF is given by a two cocycle, then an isomorphism between these two GERFs given by two different cocycles is just a coboundary between them. And if I want this isomorphism to preserve the connective structure, I have to equip it with some one forms satisfying this relation. So this is something that also Severin pointed out. Preserving the connective structure is not a property, it's a piece of structure. And this is something that happens all the time in the higher differential world, that stuff that was a property in the classical world becomes a piece of structure in the higher world. And when I have an isomorphism of GERFs with connective structure, and my GERFs have curvings, then I can define the curvature of this isomorphism. Oops. Which will be a two form on the manifold, measuring how far is this isomorphism of GERFs with connective structure from preserving the curvings. So this will be very important during the talk. The curvature of a GERF is a three form. The curvature of an isomorphism of GERFs is a two form. And finally, we have two isomorphisms of GERFs, which is this is because we are in the higher differential geometry world, and so isomorphisms have isomorphisms between them and can be compared, because if I have these two isomorphisms given by these two coboundaries, then I can relate it by a coboundary again. And yeah, I will say that it preserves the connective structure if this is satisfied. So there are some very simple constructions that one can perform with GERFs. One is very simple, just pullback. And you can also perform the tensor product of GERFs just by taking it's multiplying the cocycle that defines them. Another thing that I can do is that if I have a group holomorphism, then I can send T1 GERFs to T2 GERFs in a very easy way. It's like an associated bundle construction. And this last construction is the one that relates this to generalized geometry. If I have a GERF with connective structure, I can associate to it an exact Courant algebra, which is described. It is given by gluing this to this through the curvatures of the connective structures. And so this is something that was very well known for a long time, but what was not so clear was the geometric relation between the Courant algebra that you construct and the original GERF that you had, and that is what Collier studied in his thesis. And yeah, we will say how this works in a non-abelian context later. Okay, so now that we understand GERFs, I'm going to talk about Lie2 groups, and I'm going to try to convince you that you can understand Lie2 groups if you understand GERFs. So first of all, what are Lie2 groups? The idea of a Lie2 group is that it's some kind of generalization of the concept of a group, of a Lie group. If a Lie group defines symmetries of manifolds, a Lie2 group is going to represent symmetries of differential Boltzmanns. And I don't want to give here the full definition of what a Lie2 group is, but there are some two simple cases where this definition simplifies. The first one is that of strict Lie2 groups, which can be thought as Lie cross modules. And because they can be modeled with this Lie cross modules, a lot of people like working with them, but it's not the kind of Lie2 group that we are going to consider in this talk. The kind of Lie2 group that we are going to consider in this talk are called central extensions. And these are important because Schomer proved that the string 2 group has a finite dimensional model of this wall. And moreover, he also proved that these central extensions can be are equivalently multiplicative Chers, which is something that was already in the literature before. And that is a very good model that helps you understand what a Lie-2 group is.
Is that an equivalence of categories? Or
it is an equivalence of two categories. Yeah. And so in my next slide, I'm going to define these central extensions, but I'm going to lie. I'm not going to define central extensions. I'm going to define multiplicative Chers because it's more easy to work in this context. But I'm going to call them central extensions because I want to emphasize that this has an interpretation as a higher analog of a Lie-2 group that can define actions and that can define principal bundles and all this stuff. So let's go with it. What is a central extension? A central extension is going to be given by a Lie group T and a abelian Lie group T. And the central extension is going to be the thing in the middle, which is going to be a T-Ger over my Lie group. And this is to be thought as the total space of my Lie-2 group. And so I have to define an operation on this total space, a higher version of a product. And this higher version of a product is going to be by an isomorphism of Gers over G times C. So over G times C, I have this Ger and I have this Ger, and I want an isomorphism between them. So here then the notation is that G1 is the projection onto the first coordinate, G2 is the projection onto the second coordinate, and G1, G2 is the product. So this is going to be my higher version of a product. And because this is a higher analog of a Lie-2 group, I have to impose some kind of associativity. And so what can I do? Well, if I go to G times G times G, then I have this Ger, I have this Ger. And I have two isomorphisms between this Ger and this Ger. Namely, I can first multiply G1, G2, and then multiply the product by G3. This is what this first isomorphism does. Or I can also multiply G2 by G3 and then multiply the result by G1. And this is what this isomorphism does. So what I have to impose is that these two isomorphisms are isomorphic. So this is, again, this thing about the higher world, that stuff that was a property in the classical world becomes a piece of structure in the higher world. So it's not that we require these things to be equal, but to be isomorphic with a specified isomorphism. And then we have to require a coherence condition in this isomorphism. And well, if it's the first time that you see this kind of relation, then don't think too hard about it, but it's a natural one. So this is what's going to be, for me, a central extension. And as I said, this is all related to generalized geometry, but there's a subtlety here, and it's that the kind of two groups that really matter in generalized geometry are enhancements of these central extensions. And they are what I'm going to call connective central extensions. So if my central extension is given by a Ger, an isomorphism of Gers, and a two isomorphism of Gers, I am just going to require that this Ger has a connective structure. The isomorphism is an isomorphism of Gers with connective structure, and the two isomorphism is a two isomorphism of Gers with connective structure. And yeah, and these appeared in the literature before under the name multiplicative Gers with connection, but they were not thought of as in this language of two groups. And so this point of view is quite enlightening because it allows you to define actions and principal bundles. And yeah, I'm going to, because I care about the holomorphic world, I'm going to say that such a central extension is holomorphic if the two groups G and T are holomorphic, and the Ger with connective structure is holomorphic, and everything is holomorphic. So the first thing that comes to mind when one sees this abstract definition is what kind of examples are of these things. And we have this theorem. The first part of the theorem, I'd say it's due to Waldorf. I don't know if this was already in the literature, I don't know. But when you have an 8 invariant symmetric bilinear form from T times T to T, and well, you have to impose an integrality condition that I don't want to discuss here, but you get a connective central extension this kind. The string group is constructed in this way. And if you go into the literature, you will not find any other examples of connected central extension. And that is because we have this thing that we proved recently. And it's that if you have a connected central extension, then automatically you have an 8-invariant symmetric bilinear form that inverts this construction. So these kind of central extensions are entirely classified by the data of such a bilinear form. This is already a sign that this is related to current algebraics because, as it was pointed out before, a current algebroid over a point is just a quadratic Lie algebra. So G-nabla is a higher version of a group. I can see it as a G-nabla principal bundle over a point, even though I have not defined what a G-nabla principal bundle. G-nabla should be a G-nabla principal bundle over a point. And the way to interpret this is that the corresponding quadratic Lie algebra is the current algebroid that associated to this principal bundle over a point. And the last part of the theorem says that just with the data of the connective central extension, there's a canonical curving on this connective central extension, on this Chern. And this curving satisfies, so its behavior with respect to the group operation is very nice. How can I measure its behavior with respect to the group operation? Well, this is an isomorphism of Chern. This Chern has a curving, which is the pullback of the one on G-nabla, this the same, and I can measure the curving of this isomorphism. Sorry, I can measure the curvature of this isomorphism, which is a 2-form of D times T, and it's given by this nice 2-form. And the other property that this curving satisfies is that this is its curvature. So for me, this curving is extremely important because it's what I'm going to model connections around. And for that reason, I call it the Morel-Cartan form on this thing. Because in the classical world, you model connections on a principal bundle on the Morel-Cartan form. And yeah, it's this fact that I can measure how it behaves with respect to the group operation that allows me to do that. Yeah, this theorem, what happens with this theorem in the holomorphic context, where it's very easy. If I have a central extension, a connective central extension of this form, this is classified by a certain pairing. And this, if G and T are holomorphic, and this pairing is C linear, then the central extension will be holomorphic. And it's an if and only if. So this behaves pretty nice, as one should expect it to behave. And yeah, in this case, this curving is holomorphic. And what's good about this proposition is that it allows us to define the complexification of a Lie group. If I have a central extension of this, if I have a central extension of this form, this is classified by some pairing, and so I can take the complexification of this group, and construct the central extension that is defined by the C linear extension of this pairing. And that's my definition of complexification. Good. So now that we know what two groups are, we can define two principal bundles for these two groups. And so I have a central extension. What is going to be a principal bundle for it? Well, it's going to be given by the following data. First, a principal bundle over M for the ordinary Lie group. And then a G-Chern with connective structure over it. But I have to let my two group act on this principal bundle. So how do I define an action? Well, in the same way that the group operation was an isomorphism of Chern, I can define the action to be an isomorphism of Chern. And in this case, it's going to be G acting on P, right? So that's the kind of thing that you want to write. And since you want this to be an action, you have to impose that if you act 2 times, it's the same as acting with the product. So now you have another diagram of this form. You have this germ over P times T times C, and you have this one. And you can do the 2 things that I just said, and you require them to be isomorphic, with a 2 isomorphism satisfying a certain recycle condition would be the natural one. So this is quite natural, and in particular tells me that at G, if I have a connective central extension, then it's a principal bundle over a point, as I said before, which is the kind of thing you would like to have. And finally, I can define a connection on this thing. A connection on such a 2 principal bundle is going to be given by a pair. So A is a connection on P, a classical connection, and then B is a curving on this gel with connective structure. And what I have to do now is to impose that this connection behaves well with respect to the action of the group. How do I do that? Well, I have the action with the isomorphism of germs. I have this curving that I want to be a connection here. I can put it back here. I can put it back here. And here, I can put the more Cartan 1 form. So I can compute the curvature of this isomorphism, which is a 2 form of P times G. And I'm going to require these 2 forms to be given by this specific form. So this is kind of requiring an equivariance condition on the 1 form, on the 2 form that defines my connection. And why have I chosen this specific 2 form? Well, I've chosen it because it gives me the following proposition. If AB is a connection, then the curvature of this gel with connective structure, which is a closed 3 form on P, is going to be given by the Chern-Simons 3 form of A, plus something in the base manifold. And because this thing is closed, this means that this 3 form of the manifold is going to satisfy this Bianchi identity. And this is the Bianchi identity that you would like to have for a connection on a 2 principal bundle. And what is going to relate, and this is going to relate everything to dry symmetry. So yeah, this H that satisfies this condition, along with the classical curvature of A, is going to be the curvature of this higher connection. Yeah, this is not really what this talk is about, but it's something that I should mention. If I have a general principal bundle of this kind, then I have a Grant algebra. And it's obtained by reducing the exact Grant algebra that is assigned to this germ on P. And connections keep splitting, so everything works fine. And this is how string algebras appear associated to string principal bundles. But what I want to do is to describe, to talk about holomorphic principal bundles. And so if I have a holomorphic extension and I have a connection, well, first of all, I have not defined what a holomorphic G-nabla bundle is, but so a G-nabla bundle would be given by a gel with connective structure, an isomorphism, and a 2 isomorphism. So I just want everything to be holomorphic, including the connective structures. So if I have that kind of object, and I have a connection on it, I'm going to say that my connection is compatible with this holomorphic structure if the classical connection is compatible with the holomorphic structure of the principal bundle in the classical sense. And the curving B is given by 2 zero forms, which is also what we had for germs at the beginning. And with this definition, well, the first part of this proposition is very trivial. If I have a connection that is compatible with a holomorphic structure, then its curvature satisfies these 2 conditions. But what's nice is the converse. If I have a smooth bundle for this holomorphic central extension, and I have a connection on it satisfying these 2 conditions, then I've obtained a holomorphic structure on my G-nabla bundle. So if, say, T is trivial, and then this is already known, it's if FA02 is 0, then you have a holomorphic structure. If G is trivial, then this was also already known. I think it's in Chatterjee's thesis, but this result interpolates these two results. So it behaves very nice. And now that we have all our definitions, we can finally get to the Chern correspondence. So I'm going to start with a central extension and K compact. And I'm going to have a principal bundle for this extension, and I'm going to consider its complexification. It is defined in a very easy way once you know what the complexification of the underlying two group is. And what does the theorem says? The theorem says that there is a one-to-one correspondence between holomorphic structures on this bundle and pairs given by a connection on the, say, unitary bundle, and an omega living of type 1,1 values in real and in real values, satisfying these two conditions. So something that's interesting about this theorem is that the holomorphic structure that you get here really depends on the choice of omega. So an integrable connection is not just a connection satisfying a condition, it's a connection with an additional piece of structure, this omega. So this is again the kind of thing that always happens in the higher world. Yeah, and also if I have one of these things, I construct the holomorphic bundle, then there's a canonical connection compatible with the holomorphic structure, and this is its purpose. So this really looks like a Chern correspondence. And so this is going to be my definition of an integrable connection. It's not just a connection with a property, it's a connection with a piece of structure. And then the Bianchi identity says that this omega is going to satisfy this. So what's the conclusion of all this? The conclusion is that we can reinterpret the Hull-Strominger system as a system for integrable connection on some UR-nabla bundle that is over my original Hermitian vector bundle. And the equations are just these two equations because the rest are incorporated in the fact that I have an integrable connection. So this raises the question of whether we can find a moment map in the space of integrable connections such that its zeros are given by solutions to these equations. And if we do that, then we might be able to perform a higher subjective reduction that gives a modulated space of solutions. So that would be extremely interesting. And there's a high chance that something like that can be done because this is related to Mario, Roberto, and Carl's work on string current algebras. So that's all I wanted to say. Thank you very much.
Thank you. Are there any questions?
So should a higher moduli space exist? What kind of information would we have in this higher interpretation? So does it say something more that is not captured in a classical moduli space?
We would like that, but of course I cannot promise you that that is going to happen because we still haven't worked enough on it so as to give you an answer. But it would be interesting to use this point of view of holomorphic structures and integrable connections to try. I mean, by thinking in this way, maybe we can have a more educated guess of what's the kind of structure that this space has. And so that's all I can say. I don't have any results yet.
Questions?
So if you have one of your central extensions by B nabla T, that gives you this two group G nabla. Can you describe its Lie2 algebra?
Yeah, of course. Well, it's kind of, so I'm kind of, okay, so I'm kind of lying if I say that this is a Lie group in the classical sense, because this defines a stack over manifolds. It's not going to be a differentiable set.
Yes.
You can see it as a certain geometric object if you try to represent it instead of with a Lie groupoid in manifolds, but you can represent it with a groupoid in differential grade manifolds, for example. But another point of view is just saying, okay, what should be the Lie algebra of this thing? Well, I have G, I have T, and I have this bilinear form, which defines a Lie algebra. So it's clear that this should be its Lie algebra in whatever formalism that you're working. Well, in case someone doesn't know this, when you have a G algebra, sorry, a Lie algebra G, and you have something like this, then you can construct a Lie algebra, which is G plus T, and you have a higher bracket, which is given by the Cartan threefold.
But that would be the Lie algebra that I would get if I just used BT instead of BT nabla, right? That would just be the Lie algebra associated to a BT.
Well, the thing is, if you have a BT, G, T, then you can always improve it to one of these, and you can get one pairing this. But it's a choice. You're choosing the pairing, essentially.
Yeah.
So if you just have the central extension, then the curving is canonical. It's given by the central extension.
So the moduli space of solutions to the Hull-Strominger system, there's a map from that to the moduli space of holomorphic principal bundles, right? Where you
there are certain integrality conditions, I guess.
Yeah, it may not be a surjection, but there's a map. And
yeah.
So, so does the pre-images of a point, pre-image of a point in this map have an interpretation in terms of these two groups?
Sorry, what's the map?
The map is just, you forget about the Hermitian metric on the Calabi-Yau manifold, and you just retain the bundle, the information about the principal bundle.
Yeah, so you are talking about the fiber, the omega fiber over an A8 E8.
Yeah.
Well, that is so since I'm imposing this condition, that fiber is actually given by Kähler metrics. Well, not Kähler because you're not imposing positive definite, but it's given by 1-1 forms that are close, real 1-1 forms close.
It's more complicated than that. Yeah. Roberto didn't construct the moduli spaces.
Yeah, I have not constructed.
It's question for 1 year from now, maybe.
Any other questions? If not, let's thank the speaker again.